So we start with covariance. Covariance would simply mean the variance that exists between two random variables. So if we have two random variables, suppose x and y are two random variables with, we know what x bar is. X bar sum equals 1 to n xi divided by n. Divided by n, and xi is distributed IID from some distribution. I'll just call some finite distribution with some mean ux, some variance sigma squared x or sigma squared.
Sorry, FD is finite distribution.
Yeah.
Is that what you said?
Yeah. Something finite.
And finite
In the sense that you have a well-defined distribution on, say, for instance, normal 0, 1, minus 3 to 3.
okay, so
It's finite.
the stuff that we typically work with are
Yes.
finite distributions.
Yes.
Okay.
IIT, same thing, some mean, some variance. I just didn't want to go for a specific distribution. Not yet, at least. And we know that the theoretical covariance, the parameter, is denoted by gamma, and covariance is the expectation of xy minus the expectation of x times the expectation of y.
Is there any inclusion exclusion going on with covariance?
Yes, but if you have if you look at what I wrote, I did not write x bar y bar. I simply wrote x1, correct? If it is x bar y bar, then you have a sum, another sum, and if there is additional covariance, you've got to include that. When we do variance, simply a regular variance, if they are IID, then you don't have to account for the covariance part because they are independent and identically distributed. But if they are not IID, if there is a covariance, you have to.
Oh, it's just kind of like probability.
Yep. So you can see it here, right? If x and y are independent, I can split the joint distribution, right? If I can split the joint distribution, since you brought out the probability, right, perhaps over here. If x and y are independent, completely independent, no association between the two. X and y have nothing to do with each other. What would the covariance be?
Variance of x times variance of y, I'm guessing.
So think carefully. If x and y has nothing to do with each other, what would the covariance be?
0.
0. Because covariance measures how x varies with y or how y varies with x. If they don't have anything to do with each other, there will be no covariance. It has to be 0. So if we have two variables, we have a joint distribution. Yes, that joint distribution denoted that, and that is a two-dimensional expectation. We are trying to find the expectation of xy using its joint distribution. Extend the idea of probability over to an entire density. As Tim pointed out, that is probability of A and B is equal to the probability of A multiplied by the probability of B. Well, extend it to, a range of values, that probability explanation will be satisfied by the joint distribution. Yes, so you can write the joint distribution as f of x times f of y. Same thing, probability of A and B together, the joint probability can be written in terms of product of marginal probabilities. So integral over x, integral over y, the range of y. Maybe this comes back later on, but I'll just do it now since we're talking about covariance. I can shuffle things around and write x, f of x to x and y, f of y to y. Move that part outside. So the principle, and that erase this part. Sure. And that's something we know. When we move, we will have x, fx of x, dx of y, dy, correct? And that is the definition of expectation of y. That is the definition of expectation. So if x and y are independent, expectation of xy would equal to expectation of x multiplied by expectation of y. So I can write gamma if they are independent. Expectation of x times expectation of y minus expectation of x times expectation of y. Those two would go away, you get 0. And that is what we know. And if you have two random variables and if they are independent, the expectation has to be 0. Not the expectation of that, the covariance has to be 0. I should notice the expectation of x minus expectation of x times expectation of y. But the only time that we can split it up is that. Now it is one directional. In other words, if x and y are independent, you will have covariance to be 0. But if the covariance is 0, doesn't imply that x and y are independent. The other direction, excuse me, if, did I say it right? Let's go back. If x and y are independent, I did say covariance is 0. But if covariance is 0, doesn't necessarily mean that x and y are independent.
No statement.
Huh?
Are you telling us or are you asking us?
10.
Oh, okay.
No, 10. It's one direction. Good. Now, going back to that, we know if you write this, this would be mu sub x parameter use of y, the parameter. I'll just have expectation of x y. One can always say xy is just another random variable, w, right? And I don't know if you remember Paul, 3162, we did transformations. You know, when you have two random variables, you can find the distribution of xy, x plus y, etc. Did you do it in 3162?
I had time series.
Yeah, but did you take 3162? You should have, right?
But
Oh, that's cool. There you go.
yeah, you covered the whole book.
Yeah.
You went over so much we don't remember.
So, expectation of xy is just another expectation for random variable because I can call that w or q or p, doesn't matter. At the end of the day, it's an expectation. Do you agree? So you can call it mu x, mu y, or excuse me, mu sub xy. So the expectation would simply be mu sub xy. It's just another constant. Good. So theoretical parameters, we're set now. Now we have to go for the sample part. Can I erase this side?
And is that what you just wrote blank? Is that in general or only when they're independent?
This one or no?
Right there.
Enter. Yeah. It'll equal some number, expectation of xy. Okay, so the estimator for covariance C, that again, we're going to use 1 over n minus 1, I equals 1 to n, xi minus x bar times yi minus y bar. If you observe carefully, covariance of x and y, two different variables, will measure how one varies with respect to another. Yes, but if you put y equals x, so you have x, what will you get instead of covariance?
Oh, so the covariance. Y equals is the variance.
Just the variance. You'll get the variance of x. So can easily be noted by plugging in xi, x bar, you get the formula for variance. So 1 over n minus 1 sum I equals 1 to n, xi, yi minus xi, y bar minus x bar, yi plus x bar, y bar. Good. Erase.
So a little confused, sorry, a little confused on the reasoning on the structure of the formula because with regular variance, you put the square in, to my understanding, to avoid the negative deviations, canceling out the positive. But here we could have a case of the xi minus of one factor being negative and the other positive, and then later on them both being positive, and then some cancel. Don't we need to somehow like force them all to be positive?
No.
How do we
So
know?
covariance can be negative. Variance cannot be negative. Variance is always greater than 0. If you say specifically finite variance, then it's finite, can't be very large. Covariance, on the other hand, could be positive, could be negative, could be 0. A negative value would simply imply that x and y are going in opposite directions. A positive value would imply x and y are going the same direction.
So then they no longer covariance isn't really comparable to variance.
Variance is a special case of this. Right? Now, when y is equal to x, then you get the variance of x. Yes, when if you replace x is equal to y, then you get the variance of y.
I guess I just never really had an intuitive understanding of figure, just single variance. Standard deviation is the average spread. And then covariance is the relationship of variance between two variables. But what is a really variance? I mean, what is the square standard deviation? I mean, intuitively tell us about the data set.
Are you talking about variance or the covariance?
Variance.
Variance, okay.
I never really understood why we want to look at the standard deviation square.
So it goes back to, ultimate but I'll explain. So, okay. Distribute the sum. You have 1 to n xi yi minus sum 1 to n xi y bar minus sum 1 to n x bar yi plus sum 1 to n x bar y bar. Yes. So 1 over n minus 1 sum 1 to n xi yi, y bar is a constant. That would leave behind sum I equals 1 to n xi, correct? Sum I equals 1 to n xi is simply n x bar. Same logic, x bar is a constant. Sum I equals 1 to I equals 1 to n yi is n y bar. X bar is a constant, y bar is a constant, so you're summing n of those n x bar y bar. Yes? Go on, go on. That's all we have. And that we'll have n x bar y bar. If I take n out of that square bracket, I would have n over n minus 1. 1 over n sum I equals 1 to n xi yi. Yes. Minus x bar y bar. Agree? Well, going back to, can I erase this? Tim?
Yes.
Going back to the weak law. What does the weak law of large numbers suggest? It suggests or shows that x bar will converge is an improbability or a distribution. Probability to ux. We did this. Yes.
But that also implies in distribution.
Yes. Yes, it is. And
Not the other.
not the other way around. Y bar will converge to mu y. Yes, we know that as n approaches infinity. Good. Now, earlier when I was talking to Tim or explaining the deviations or use of standard deviation, and I said, oh, x times y is just another random variable. I can call it w. Yes. If, for instance, I said w is x times y. Good. Then gamma hat would be n over n minus 1. 1 over n. Each xi times yi would then be wi. Do you agree? So I can write this as I equals 1 to n wi minus x bar y bar. Agree? But then that is nothing but w bar. Do you agree? If that is true, then using the weak law again, we know W will approach, oh, excuse me, W bar will approach
UW.
mu W probability as n approaches infinity. Right? I'm just going to replace W by xy. But together, you can't split them up. So in terms of notation, xy bar will simply approach mu xy as n approaches infinity. So I'm saying that this number will approach mu xy. Good. So we want to know what would gamma hat or psi approach as n approaches infinity. I'm going to take the limit move the n to the denominator. I'll have 1 over 1 minus 1 over n. Yes. If you rewrite this, you'll get n times n minus 1. W bar minus x bar y bar. Yes. One over limit n approaches infinity, 1 minus 1 over n. Limit n approaches infinity, w bar, minus limit n approaches infinity, x bar, y bar. Bring down continuous functions and start to apply the limits individually, so I can apply the limits to each of them. What would the limit here approach?
W.
Mu w, but if I replace w by x, but it would be mu x y, yes? And limit n approaches infinity x bar would be mu x. Limit n approaches infinity y bar would be mu y. And the limit of that would be 1. Yes? So we're saying gamma hat will approach the probability to mu xy, mu x, mu y. Yes. But what is, yes,
With the last limit, second row, would that be limit X bar times limit of
Yeah,
two.
you can distribute that.
Oh, okay.
Yeah, I just didn't write it separately. You can distribute that. What does the right hand part or right over here it become? What is it? Mu xy minus mu x times
Feels like it should be 0.
0. Look at what we did at the beginning today when I first started this.
Oh, it should be the theoretical.
It will be the theoretical value. In other words, gamma hat will converge to gamma in probability as n converted inverse. So the sample covariance is the estimator for gamma, the theoretical covariance, the actual parameter.
So XY bar is not necessarily the same as X bar, Y bar.
No, definitely.
Okay.
No.
Yeah, that,
Same thing, go back to the definition of covariance of x comma y, gamma. Expectation of xy minus expectation of x plus
Gotcha.
expectation of y. You can't split it up. Expectation of xy stays intact as long as x and y are not independent.
makes a lot of sense. Thank you.